In the next couple videos, we're going to take a closer look at the relationship between our electric field and our potential difference V. So recall that previously we had said the potential difference between point A and B is independent of the path taken. So in other words, we can say that if we have some potential VAB, VBA, that is going to equal to negative VAB, again, regardless of what path we've taken. So what we can say then is if we sum those two voltages, so if we have VBA plus VAB, then that should be equal to 0. Well, we can use our previous expression that related V to electric field to say that VBA is the integral, well rather negative the integral from B to A of E dot dl, and our VAB is negative the integral from A to B of E dot dl. And again, from looking at the far left side of this equation, we know that these two voltages should add up to equal to 0. Okay, so now what we can do is we can sort of think about factoring out that negative, so this becomes positive, and we have the integral from B to A of something and the integral from A to B of something. So what we can say is that's just equivalent to our closed line integral, so our circulation. So we're integrating along this path of ABA, and we're integrating E dot dl. And so we're saying that that is equal to 0. So we're saying the circulation of E around some closed path is equal to 0. So our line integral of E around a closed path, so important that it needs to be a closed path, we need to be ending where we started, is 0. And so the implications of that is that there's no net work done in moving a charge along a closed path in an electrostatic field. So no net work done in moving a charge along. And again, it's key that this is a closed path in an electrostatic field. Okay, well, we can actually sort of rearrange this equation a little bit by using Stokes Theorem. So Stokes Theorem, which we looked at when we were considering our vector calculus, says that if we have the line integral around some closed path of some vector field dot dl, that is equivalent to the surface integral over the surface enclosed by that closed path of the curl of that same vector field, so del cross E in this case, dot ds. And so from above, we know that that line integral has to be equal to 0, so that means that surface integral is also equal to 0. Now the only way that these integrals are going to be equal to 0 is if the integrands themselves are equal to 0. So that's this E dot dl or this del cross E. So therefore what we can say is that del cross E, or the curl of our electric field, is equal to 0. And so now we've come to our second of our 4 Maxwell equations. And so this is Maxwell's equation for electrostatic fields. And so you'll notice that there is a slight difference between this equation and the one we looked at way back when we first introduced electromagnetics and Maxwell's equations. And that's because this is for for static electric fields. And so the two box equations are just different forms of Maxwell's equation. So here we have the differential form, similar to with our first Maxwell's equation, and here we have our integral form. And so which we use depends again on the situation and what information we have available. One thing to sort of highlight again that we talked about a while ago is vector field notation. So if a vector field satisfies either of those two equations, then we can say that that vector field is conservative or irrotational. So if vector field satisfies either boxed equation above, then that vector field is said to be conservative or irrotational. So not terribly important to know that, but just a little bit of terminology so you're not confused if you do see that.